We live in a digital world. As such, network security then becomes about protection of digital signals, namely ones and zeros, as these digital signals are going between a transmitter and a receiver over a network. There are a number of underlying fundamental building blocks that are used in most of the cryptographic algorithms out there, and they process digital signals, ones and zeros, and combining these primitives allows us to build various cryptographic algorithms. Some of these primitives are pseudo-random generators. Now, actually, it would be good to have truly random numbers for some of these algorithms, but in practice, pseudo-random numbers are good enough. What do we mean by that? A pseudo-random generator generates streams of ones and zeros that are not actually random, but for most intents and purposes, they appear random. If you do various statistical tests on them, they look random. It's hard to tell that they are not random and follow some kind of deterministic algorithm. Besides pseudo-random generators, other primitives you would find in cryptography are ciphers. Block ciphers are where blocks of bits are encrypted, and then the results are concatenated together, but each block is processed separately. Stream ciphers, on the other hand, are where you have streams of ones and zeros going into the cipher and then a stream of encrypted ones and zeros coming out. The important thing about ciphers is that it needs to be hard to do the reverse, so that if you have ciphering happening at the transmitter and then someone other than the intended receiver receives this encrypted data, it would be hard for them to decrypt the message. Only the receiver is able to decrypt it properly. And one way this might be done might be if the transmitter and receiver share a key that only the receiver then can use to unlock the message. Another security primitive that is found in cryptographic algorithms is a cryptographic hash. In order to protect the integrity of a message, the transmitter might compute a cryptographic hash of the message and attach that to what is sent, maybe attach that to the encrypted data. On the other side, the receiver can then check to see if the received message, when it's hashed, it matches the message digest that was sent along with the message. This works because cryptographic hashes are designed to be hard for an attacker to find another message that produces the same hash. So if an attacker actually has modified a message, it will very likely have a different hash. It's very hard for an attacker to, after modifying the message, to then make some additional modifications perhaps, such that the resultant message would produce the same hash. So the hash is not going to match. Now all of these security primitives can be combined in various ways, and they are done so in different cryptographic algorithms, but they are not easy to do. It's difficult and tricky to apply.